All right, let's jump right in. We are going to talk about something that, believe it or not, you do all the time, probably without even realizing it. It's all about spotting the weird stuff, right? Finding that one thing that just doesn't fit in a huge sea of data. I mean, you know the feeling, don't you? You're just casually scrolling through your credit card statement and then bam, there it is. A charge from some store you've never heard of, in a city you've never even been to. Your brain just goes, whoa, hold on, that's not right. And right there, in that split second, that's it. That's anomaly detection. That gut feeling is the very same principle that powers some of the most critical technology running silently in the background of our lives, from our banks all the way to our hospitals. So, to put a formal name on it, this is what we're talking about. It's the whole process of finding things that just don't follow the rules. And it's absolutely crucial for things like stopping fraud, like in that credit card example, but also for catching cyber attacks, or even making sure a product coming off an assembly line is perfect. But here's the thing. Weird isn't a one-size-fits-all kind of deal. It turns out data can be strange in a few different ways. So, let's break down the three main flavors of anomalies you're likely to run into. So first up, we've got the most obvious kind, the point anomaly. This is that one data point that is just wildly different from everything else. You know, it sticks out like a sore thumb. It's that $10,000 charge when you usually spend $100. It's big, it's loud, and it's pretty easy to spot. Okay, now this is where it gets really interesting, because context is everything. Think about it. A $200 transaction, by itself, totally normal, nothing to see here. But what if that same $200 charge happens at 3 in the morning for someone who you know only shops during business hours? All of a sudden, that perfectly normal data point starts to look really suspicious. It's the when and where that makes it weird.
And finally, we have the sneakiest type of all. With this one, if you look at any single transaction, it looks perfectly fine. A few bucks here, a few bucks there, no big deal. But when you zoom out and see this sudden swarm of tiny, normal-looking charges all happening at once, the group itself becomes the red flag. The pattern is the real problem here, not any one data point.
So the big question is, how do we actually catch these different flavors of weird? Well, you need the right tools for the job. Think of it like a data detective's toolkit, where each tool is designed to find a very specific kind of clue.
The first things in our kit are the tried and true classics. These are the straightforward statistical methods that have been around forever, but you know what? They're still incredibly good at finding those really obvious point anomalies.
The z-score is a perfect example. It's basically a really quick way to ask, just how far from the average is this thing? If the answer is, say, more than 3 standard deviations, we flag it. It's amazing for data that behaves nicely, in a perfect bell curve. But it can definitely get tripped up by more complex, messy, real-world data.
And that's exactly why the simple magnifying glass isn't always enough. For those trickier contextual and collective anomalies, you gotta bring in the big guns, the AI bloodhounds that can sniff out those hidden patterns that humans in simple stats would just walk right past. So let's check out a couple of these AI detectives. On one side, you have something called an isolation forest. It's fantastic at finding global anomalies, things that are weird compared to the entire data set. It works by basically seeing how easy it is to single out a data point from the crowd. Real anomalies tend to be loners, so they're super easy to isolate. Then, on the other side, you have the local outlier factor, or LOF. This is more of a local detective. It doesn't care about the whole data set. It just looks at a point's immediate neighborhood and asks, hey, is this guy way weirder than his direct neighbors? All right, now for a really clever, almost backwards approach. Imagine this. You train an AI to be a master forger, but you only ever show it pictures of cats. It's going to get insanely good at drawing cats, right? But then, what happens if you ask it to draw a dog? The result is going to be a total mess. That's the basic idea behind a technique called autoencoders. So here's how it all goes down. First, the AI trains only on normal data, learning to copy it perfectly. It does this by literally squeezing the data through a tiny information bottleneck and then trying to rebuild the original on the other side. Now, for normal data, the copy is almost perfect. But when an anomaly shows up, something it has never seen before, it totally fails to rebuild it properly. And that failure creates a huge reconstruction error, which is like a giant flashing neon sign screaming, hey, anomaly over here. Okay, so we've got our tools, we're out there finding anomalies. But how do we actually know if we're doing a good job? This is where things can get seriously counterintuitive and fast. I mean, this just sounds crazy, doesn't it? In almost any other field, 99.9% accuracy is a home run. You'd be celebrating. But in the world of finding anomalies, it can actually mean you have failed completely.
Just think about it for a second. Fraudulent credit card transactions might make up, less than 0.1% of all transactions? So a lazy model could just predict normal every single time, and it would be correct 99.9% of the time. But it would also miss every single fraudulent charge it was built to find.
And this table just lays that trap out perfectly. Look, we have 10,000 transactions, and only 10 of them are actually fraud. Our model just guesses normal for every single one. What's the result? Yep, 99.9% accuracy, but we've detected exactly 0% of the fraud. It's a perfectly accurate and yet perfectly useless model.
This is precisely why we need better scorecards. We have to talk about two key things: precision and recall. Precision asks, of all the alarms we raised, how many were actually real? This is all about not bugging your customers with false alarms. Then you have recall, which asks, of all the actual fraud cases out there, how many did we manage to catch? And this is about not missing those huge, costly events. It's always a balancing act between the two.
So, let's bring this all back to the real world, because this isn't just some abstract data science puzzle, right? These ideas are working all around us every single day in some incredibly important ways.
It's literally what stops fraud on your credit card. It's what detects a hacker trying to break into a corporate network. It's what ensures quality control in a factory by spotting a tiny defect on a production line. It's even being used in hospitals to monitor patients, flagging subtle changes in vitals that could be the first sign of a serious problem.
And in the real world, there's no single magic tool that solves everything. The best, most robust systems use what's called an ensemble approach. They combine multiple different models, maybe a z-score for the obvious stuff, an isolation forest for global outliers, and an autoencoder for weird patterns, all working together. It's like having a whole team of detectives, each with a different specialty.
Which kind of leaves us with one final big question to think about. We've gotten really good at building tools to find the anomalies we already know about. But as our world gets more and more complex, and we generate more data than ever before, the very definition of what's weird is going to change. The real challenge isn't just how we find anomalies, but figuring out what the next critical, unexpected pattern is going to be that we need to look for.